So hello everybody. I'm Francisco from Portugal, and I suppose all of you are interested on how to type language into the HTML. So I tried to sort of give you an overview how this works, and basically to stimulate ideas on what you could do with this. Our basic approach is that we convert text, that is text in written form for the time being. So this is not actually meant to be used in speech, which is a slightly different problem. Which I will detail this a little bit later. So we assume text, and we create a number of assumptions when we convert text to become useful for input to the CLA. Maybe I first get a slide that I have here to show you this. So precisely. So the assumption that is basically behind all what we are doing is that as the HTML theory creates, from our standpoint, the constraint that everything that has to be processed with the cortex has to have the format of an SDR. So the goal of this is, next to the fact that we can directly fit the text into the HTML, it's also that there are some advantages, of course, with the SDRs. They are, so to say, resistant to all sorts of noise. They have the possibility to represent things in a very expressive way, in a semantic way, so that the actual converted information, or the converted symbol, in our case, always tries to contain as much of the information as possible. So this is a very abstract view of the assumption that we are working with, which is, as language is produced by the neocortex, and as the neocortex uses only SDRs as input and output, there has to be, if you want, a place in the cortex where the smallest unit that actually contains some meaning, that expresses or describes an inner concept that we have, this has to appear somewhere. And especially if we produce language, or if we decode language, which is called, so to say, the externalization or materialization of the concept that we have in mind, there needs to be some sort of layer where a representation of a word, which is the smallest part, so to say, of something that can carry meaning, comes to existence, if you want. So this is part of some theoretical approach to investigate this deeper. There are several problems that are related here. So one problem is, for example, the so-called semantic grounding, that at some point you have to tie this semantic description in the SDR, you have to tie it to something concrete, and at the time of language acquisition, there is nothing there to tie it to, because the baby, so to say, has no language. And there comes the concept that one can create the semantic grounding by using all the other senses that basically create the very first patterns that are used to specify the very first words. And over time, there are more and more word patterns, if you want, that are stored. And at some point, there is a switch where you use actually words to define the semantics of words, which creates this idea of using contexts to describe words. But there has to be, in the very beginning, when there haven't been any contexts, the only information that was available was, so to say, touch, sound, and very primordial inputs. So what we end up with is a representation that has the characteristics, so to say, of being a sparse representation. What you see are on the left and on the right sides 2 words, the word organ and the word piano. And they have been converted into the word SDRs. We call them fingerprints, by the way. And the fingerprint for the word organ and the fingerprint for the word piano, as you can immediately see, have certain similar aspects. There are some sort of clusters that appear in both of them. But there are also differences. And every point in our representation corresponds to a so-called context. And the context is a collection of words with which this word has appeared historically, so to say. As you can imagine, this map, if you want, is a very specific thing because every individual creates it, so to say, interactively with the world. So everyone, in fact, has a different, at least slightly different map, depending on what your experiences were and what you have, so to say, heard so far or read so far. The interesting aspect is that although this is a very, so to say, private representation of the language universe in the brain of each of us, there is a direct correlation that allows us to communicate, because if I externalize some language pieces, so to say, using my map, and I suppose that someone else should at least partially identify some information in this, there has to be an overlap between those maps. And what is a very nice effect is that the distributed and especially the sparsely distributed representation allows to make these sorts of overlap at all levels. So you can even work with 2 different maps. And if the 2 maps have sufficient overlap, there will be a way of computing the similarity between fingerprints produced with those maps. So in a very simple fashion, for example, if 2 people speak the same language, they have already a large part of this map as an overlap, and therefore it will be pretty easy for them to have a conversation. If 2 people have even a different externalization, means language, they will have a hard time to actually communicate. But there is still regularity because a third person who is able to speak both languages, therefore can map between the 2 maps, will be able to translate. And as you see, this already shows that there are 2 aspects here. So one is to get the information in this mapped form, if you want. That is what we call, by the way, semantic folding, which means that every word that is represented by this way has all the knowledge, if you want, about its semantic universe packed into the encoding. So, and this is important because the HTM per se doesn't know anything. It does just work with the impulses that come, so to say, from the different inputs. But to have a correct interpretation, there has to be, at least for language, obviously, the semantics of the data that is coming in has to be packed in the representation. Yeah, as I said, a very fundamental approach is to have the mapping aspect on one hand and the similarity operator at the other. So you can basically decompose most, if not all, language-related issues, but you can decompose them into analogy calculations and sequences of analogies. And because the information is, so to say, semantically annotated, if you want, you can do this without any other prior knowledge. So another interesting aspect is that with this representation that is in the internal format, it's a binary format, so these are binary vectors. Specifically, they have a length of 16,000 bits, so it's 128 by 128. The fact that they are round is just sort of artistic approach to this, but in principle, mathematically speaking, they are squares. And what is specific compared to other encoders that you can use with HTM is that there is topography. So this is one aspect that we have found is very important in doing this mapping, is to make the representation topographical, which means that even if you look at the vector, so to say, as a long string, there are still the neighborhood relationships between the bits follow the fact that they are arranged in our case, square. The reason why this is important, again, I need an illustration. So I hope you can read it. I mean, it's not necessary to read everything. The idea is that in a distributed representation, every bit has a meaning. So it's not like if we have, for example, the dense encoding of the word cat. This is basically following the ASCII rules. You take the characters, use the bits of it. Nothing in the bits actually tells you what this item is. In this case, when you have bits that are tied to meaning, you see in the first line, you see correct bits. There are things like it's red, it's green, can walk, can fly, can swim, and so on. So all the characteristics that the actual inner the inner image, so to say, of a cat should be associated with are encoded in bits. And I don't know if you see this, there are several of the bits that are set to 1, which means that this feature actually occurs with this instance. So as we know, with the SDR representation, we can drop several bits without actually changing the fundamental part of the information. So, for example, if I drop, I don't know what was dropped here, is red, or can swim, the remaining bits will probably, or most probably, even still point to the same animal that I wanted to represent before. And the thing is, the more of those animals I've seen, the more resistant I become in dropping bits. So we all know this famous picture of Abraham Lincoln, where you can actually bring in the distortion up to an incredible point, and you still see this. If you show the same phenomenon to young children, they have a harder time in doing this because they obviously have not such a large context as adults might have. But there is another aspect. It's not only about dropping bits, it's also about images that shift as a whole. So the problem, if I have, so to say, a random distribution of the characteristics where one semantic feature has nothing to do with the semantic feature to the left or to the right, I have the problem that if the whole binary word sort of shifts, which you could imagine as inside, for example, when you make saccades, you have a sudden shift of the whole image, then it becomes not really, for this problem, random distribution of the bits is not really stable, because you can shift into something where you get completely different semantic links here. So the problem would be to arrange the bits in a way that even if you shift up to a certain degree, the main semantics behind it should stay, so to say, correct. And the easiest way of doing this is by grouping those bits in a way that the bits that occur often together start to get grouped topologically, which means in this case all the bits that occur together because they are pointing at fish, for example, should tend to be on a specific area. Dots that point to birds should be in an area, and suddenly we have also this dynamic noise where we are more resistant for, and this is just by arranging it topographically. And there are in fact a number of mechanisms, I think, like Hebbian learning, for example, that could be used to show that this is a process that can be done using neurons. In fact, we use some old-fashioned artificial neural networks to do this, but I'm pretty sure at some point that we can find a way on how the HDM layer itself could, so to say, perform such an action. But for the time being, it's still, so to say, theoretical. So what can we do with these representations? We can compute things like we can add and subtract. We have a binary representation. We use Boolean operators. And I can, for example, now subtract piano. That's the one I've compared before. And I see that here, in this area, there are still points remaining. This means not all the points in the representation of organ are actually matching with piano or the instrument aspect. So this comes to the level of that there are multiple meanings that can be encoded into a single representation. Obviously, in language, we have this issue with ambiguous terms, where in reality, I think about half of the terms that exist are ambiguous. So this view basically that helps you to visualize what you can do with SDRs and how they behave. You can use this on our website. It's available there together with this tool that does a very simple operation to find out about all the different meanings that can be captured in one of these representations. So again, I've entered the term organ, and here the system found several ways or several information or topics within the word organ. So it found one topic that is muscle, and if I ask for similar terms in this context, I will show you how this is done shortly, then I get all sorts of terms that relate to the body. So obviously the organ is the sense, so to say, of a body organ. If I go here and select the topic cluster piano, I get all sorts of instruments, and all of these meanings are basically encoded in this one fingerprint called organ. And what I can do now is that I can have a look at all these different sub-meanings that I have in this representation. So I can, if I subtract piano and I now compare it to the other word was muscle, I see that I have also an overlap here in this region because organ also shares this. So this basically shows why the encoding actually captures all these different meanings. And the mechanism to find the existing meanings for any word that is represented in the system is very easy by just using, again, a similarity function. So we take the word, we ask for the most similar other word, we take the representation of this other word, it is a binary representation itself, and we subtract all, so to say, all the dots that are from this second representation. Then the remainder of what organ minus the other points is, we ask again what is the most similar word. We find the next largest cluster where the first word is piano, and so on. And like this, we have a very simple binary operation, a sequence of binary operations to find out about any word. And again, you can go to the website and you can type in a lot of words and find out what the different categories are. And the labels that you see up here are actually not really labels, but they are simply the topmost word that corresponds to the similar words for a specific meaning of a word. So this is also generated. So, and for those of you who know or have worked in NLP areas, you know how hard good labeling of clusters could be. So here it's just a byproduct, so to say, of doing this. Yeah, so all of this, basically what you see here and much more can be seen on our API. Here we have, if you go to API code.io with the browser, that's what you see. And here you have the different sections. So there are endpoints for Retina. This is a REST service, by the way, so it's straightforward to use it. We have operations with terms, so we can ask the system for a term. For example, if I open such an endpoint, I get the information about the endpoint, I get the different types, all the documentation is there. And what is very nice is that you have here a form where you can interactively play with the functionality. So here you can choose, for example, there are here 2 retinas. That's maybe also a point to note. We call them associative and synonymous. So the example is if you bring in Albert Einstein with a synonymous retina, if you ask for similar terms with a synonymous retina, you will get results like Niels Bohr or Heisenberg and so on. If you ask for similar terms with an associative retina, you will get quantum theory and energy and things like that are associated with the term. So I would call this, in the sense of similarity, these are the 2 limits, outmost limits of how you can use similarity, because similarity is not a very sharp concept. It has, in different contexts, it can have a slightly different use. So you can basically, for whatever operation, choose, in this case, between those 2 retinas. These are basically this mapping algorithm. So we have 2 different maps that we offer here as a choice. So here I can put, for example, the word from before. This is just paging information. The get fingerprint is, I can show you in a second step, that's basically I can also get the numerical representation of this word. And if I just use it, I get here the actual REST code that I can then so to say copy in my source code if I want, and I get a JSON formatted answer, and in this case you get the meta information that is stored with this fingerprint. So you have the word, you have the document frequency, and the post type, which means noun, word, and so on. This is very often helpful to select from results and to say I just want to see the nouns for this or just the adjectives and so on. And if I actually say I want the fingerprint, what I get is a list of indices where every position, so the positions from the frame are numbered from 1 to 16,384, and each number here is a 1 in the bit. So this basically is a method of compressing the output a little bit. So the functionality to just go through is the term. Here you get the information about the term itself. Here you can ask for the contexts of the term. So if I input here Morgan again, and we try out, I get a JSON result that gives me all the similar terms, gives me the context. That's what you have seen in the line of the different types of meanings. So this is a simple text to see are there several meanings in a word, and with a second call you can get for each of the contexts the similar terms. So I can say I want a similar term for the second context, for example. And here I get for the church, the organ context for church. Yeah, so these are the term features. Then we have the same thing with text, and we have also already some a little bit more sophisticated functionalities. So text basically does the same. It gives you the fingerprint for a whole text, so all this procedure to actually bring the word fingerprints together to form a unified text fingerprint are done in the background. What can be interesting for some applications, for example, is the keyword function. I can give you an example here. This is Spanish. English. So So if, for example, I take a piece of text and I input it here, what the system does, it basically creates a fingerprint of the piece of text, and then it goes out and looks which is the least number of words needed to reconstruct a fingerprint that is most similar to the fingerprint of the whole document. And this is kind of the opposite way as typically keywords are extracted, because one uses statistics to find which is the most probable one. By reconstructing it, it's quite interesting that the results tend to be pretty good. This is Albert Einstein. Yeah. Because I used to play around with this, I never know what I potentially have in the copy buffers. I trick myself out from times to time. Yeah, so this is a function that already contains a lot of sort of computation with the fingerprints in the background to make it easier to do things like extracting keywords. You have here a tokenized function where I paste my very same text, and what it does, it decomposes the text in all the tokens. So this is nothing special in principle. This is here just for convenience, so that when your program basically inputs some text, you can be sure how the system actually reads it. Yeah, that's because tokenizing is quite a strange art. So there are like 2 million ways of tokenizing text. So to be sure that you can tokenize a text in the same way when you feed it, for example, in the HTML in the backend, to be sure how it is actually tokenized by the system. Then you can slice. This is also a very useful functionality, because you can have texts where you have many different meanings, so to say, or topics covered in a text. And usually it's very helpful to cut the text in little pieces where you have only one meaning in one snippet of text. And this is done by this function. This basically is, again, we always use the fingerprint approach as such. We create a gradual fingerprint while going along the text. And when from one step to the next, the change in number of points of the fingerprint is bigger than a certain threshold, then we say we have identified a change in topic, and we cut the text there. And this is pretty convenient if you have large texts and you want to create very distinct fingerprints for the text. You can just throw it in here, and you get a JSON return where you have always one snippet, and you can also ask for the individual fingerprints in every snippet if you want to continue the calculations. And the whole thing can be done in bulk, so you can basically send many texts and do the very same operation on many texts, and you get a then larger JSON in return with all the results. Then you have the same functionality that we had with terms before can also be done with expressions. And with expressions, you have a very flexible way of linking functionality together. So an expression could be, for example, that you have a term and you subtract a numeric fingerprint at some point. So in the expressions, you can input terms or text or fingerprints as items where you make ands and ors and subs to compute things. And it's interesting that this is a very small but very flexible set of operators that allows to do quite a lot of things. And very often the, so to say, very naive approach in trying to compute something is actually the correct one. So you don't actually need to be a linguist to use this, and that was also partially the goal. And so the result is given back as a numeric representation, and I could, if you don't get seasick, I copy this fingerprint in numbers, for example, just to give you an example. And now I can ask for similar terms. I can input any fingerprint into this function, and I will get, hopefully, a list of similar terms and their frequency for this fingerprint. So I don't even need to remember what this fingerprint was. I just throw the numbers in, and I can get this is obviously something with cars. Okay, so this is so the expressions need a little bit of so to say habit to use them, but they are very flexible and I think consistent in the way how they are used. And then the most important of all is, of course, the similarity function. The similarity, you can use it to basically compute the similarity between any two items, so any two words, text or expressions. And what the similarity gives you back, I'll just copy the example here, is a list of distance measures that you see here. So there are some basic numbers that you get, so the size of pixels on the left and right side. You have the overlap percentage on left in right and right in left, and the absolute number of overlaps, and then you have distances like Euclidean distance and Jacquard distance, so you can go to...
What's the left and right and left referring to what?
In percentages. So
what's the left and right mean?
That
right
means how many percent of the how many dots represent the percentage compared to the number of dots in the right and vice versa.
Right being one.
This is
basically you just look
the first and the second.
So you don't get the comparison of two words in different.
Yeah. So the first word is theoretically the left.
I see.
And this is a residual from early days when we had this actually graphically shown. The idea is that the overlap is that the absolute overlap is not always indicative. So if you have one word that is very frequent, it has a lot of dots, and another word that is very infrequent.
Just because your words are not equally sparse.
Exactly, because there are words that occur more often and others don't. Yeah. So the only way in actually equally sparsing would be to increase the training corpus so far that the least occurring words that we see should have the minimum sparsity. But so far, it's easy to handle, so to say, the fact that they are between 2% and, I don't know, 0.01% in field rate. And of course, very often you can use the fact how frequent a word is. You can use that also in your algorithm. So you can, for example, on purpose choose the more frequent words if you want to give a more general answer to something, and the inverse also. So the reason why we try to give all these numbers is basically because it also depends on what you want to do. Yeah, some problems are easier to solve with the overlap or to characterize with the overlap. Others are easier to characterize with the cosine similarity. But basically, they should all be coherent up to a certain point, depending on what the algorithm behind the distance is. And to have it arranged like this also gives us the possibility, in case that we find out that there is yet another distance measure that could make sense, we can introduce it without disrupting the rest of the API. And then I can do the very same thing also on a graphical level. If I want to give feedback to my users, I can put the expression here, and now I get, so to say, the graphical representation if that is needed. And again, this can be done in bulk. Yeah, so this is the current, our 2.0 version. This has been tested by a number of users with really hard load, so I'm very confident that this is extremely stable at the moment. What might be interesting to you is another development that we will expose very soon, and that basically goes in the direction that we wanted to extend the usability of the numerical fingerprints. So in the way how we have trained the retina so far, we have trained them separately for every language, and every retina had, so to say, its own topology, because this is Hebbian learning. You never know how the actual topology will look like, and in fact it doesn't matter as long as it is in itself consistent. But if you want to go, for example, from English to French, it would be very convenient if the word, for example, for biology in English would have the same fingerprint as the word biology in French, because that would allow you to do all the operations that I've showed you, and especially the similarity would be, of course, interesting across languages. So we have ended up in finding a way in doing this up to a certain point, so we're still refining it. And you can see on this application, it should have still this Einstein text. No, this, see, it's a copy buffer mess. So, take this again. And if I bring it here, what happens is that the document fingerprint of this is generated, and this document fingerprint is then submitted to 4 different retinas in 4 languages, and we ask for the similar terms for this numerical representation, and as you see, there is quite a good correlation in the different languages with the topic. And yeah, there are simply, I mean, this is not translation, we are not to be misleaded, so we are not translating anything here. We're just taking the representations and we try to normalize them across several instances of retinas, and to allow, so to say, cross-domain mapping also. Because what we could do, of course, also is not to use this not only for languages, but to use this within a language and topics. So we could say that there is one retina that knows in general about healthcare, and one retina that is a cardiology specialist know-how that is captured in the retina. By having a bridge between them, you could give like gradual answers to questions and stuff like that. So there are a lot of possible applications for this. And another, so to say, outlook on what we are working is what we call a fingerprint editor. This is basically a Photoshop for neuroscientists. The goal is basically that you can enter...
So if I draw a picture of a cat, I'll get a cat.
Yeah, exactly. That is version 2.0.
Yeah.
So the idea is you start off with a certain pattern, and you get the context terms for this pattern. And by coming here and saying, okay, now I want to get rid of a number of pixels. So one of the issues is there are no drawing tools, so it will take forever now to get rid of the pixels, but I did it a couple of times. And what actually happens is that you see after each pixel, it recalculates, so to say, the similar terms, not for the expression anymore, but for what is on the canvas. And you can actually spot the moment where, for example, you move from organ, the context of body organ, to organ in the context of musical instruments, because there are the new contexts basically coming in from the lower end. And the practical application for this is that you can use fingerprints to classify information. So you can try and get sort of the skeleton of a bunch of documents by making a fingerprint of every document, making an AND of those fingerprints and finding out which pixels stay the same. And this ANDed set of documents could be like the skeleton of a classifier for what documents should be classified in this part. As this is all, so to say, a bit blurry, it could be helpful to have the possibility to add or remove single pixels to make this better. And the second aspect is that that will come before we release it. If you put the mouse over, what you should get is like a word cloud on what concepts are under this area. So this gives you also a local feedback on which pixels you are allowed to edit. Yeah, so...
That's a work in progress, you said? That's a work in progress?
Yeah, so this is basically something for front-end wizards, and we have a guy working on this interface, because this is mainly an interface issue. So this basically uses the API as it is, and it tries to give functionality in the front end. Yeah, so I hope you have sort of a more a better understanding of what we try to do and what you could do with the API. If you have any questions.
Are the results from the API stable over time? If I ask for the composition today, is it going to get the same result in a month from now?
So the berry representation, you mean? In principle, as I said before, as soon as the underlying 2D map changes, in principle, the pattern will change. So we will make sure that there is always the possibility to sort of step back to older retinas to get the representation. Nevertheless, I would suggest not to actually, so to say, locally store this information, because if the retina evolves, you could not take advantage of, for example, being more precise or having new words that come in. So the best way in actually capturing a fingerprint is by capturing the query by which you have created it, because then you can create it with whichever retina is there, and very soon you can create it in French too, which is okay. Jeff.
So I want to get back to the issue of topology, because I think about a lot. So you said, well, you talked about the advantages of having the similar meaning of bits co-located, because it makes a shift in variance. But why does that matter? I mean, when is there going to be a shift, and how does that practically make a difference? I didn't see that.
Yeah, simply by the fact that in the real biology, you have many bits that you don't absolutely control, and there could be situations. So I simply think that there could be many situations where the whole image shifts.
Well,
so to say.
Okay, so I'm not sure that's true, but let me ask you: does it make a difference in your implementations here? Does it come into practical play anywhere here?
Yes, because when you calculate the distance for a whole representation, you get, so to say, smaller values for bits that are otherwise not correlated.
If you use supertized overlap metric that you talked about yesterday, it wouldn't matter.
For the pure overlap, it won't matter.
Yes, obviously, if I want to do something, basically you're saying if I use a distance metric that assumes that bits near each other mean something, then it'll matter. But
the point is, it is helpful for similarity calculation. If you have no, so to say, possibility to have, so to say, shifts in the representation that are, so to say, lateral in the meaning. Yeah? So this is on an abstract level. The similarity is different. The only similarity, if you have randomly distributed bits, is in actually looking which bits, how many of the bits actually overlap.
Yeah, I guess it's just not clear to me how that practically going to make a difference.
If you sparsify this, right, and you start to lose a few, then losing a few in a big cluster will have less of an effect if they're grouped together like that.
But even
this
if
is not necessarily
if I randomize the location of all these bits and I lose the same bits, I'll have the same.
This is true. For the flipping bits, it doesn't make a change.
But I'm asking, it's the thing I'm struggling with. I'm not trying to be contrarian. I'm trying to understand if I need to do this or understand it. It's a question of, you don't get a shift like this. Numbers don't shift over a little bit. It's not going to happen.
No, but at the input you can shift.
But it's a misleading way of thinking about inputs. And we're talking about vision and stuff. We don't do that. We memorize transitions. We don't. The picture on the optic nerve never shifts or something like that. But anyway, in this case, it's not clear that I would ever have one of your fingerprints that shifts. It's just, I can see what the calculated
the place
distance
where we
method-
actually use it currently is that if we have to sparsify, so if you do large ores of fingerprints, of
You
course
could
the
use this- You could
representation
use this as a way of sparsification. you could say.
exactly without losing. So it's
Yeah.
a way of semantically compressing.
Do you
can
do that
reduce
now,
it.
or do you do that now? or
We
not?
do that now.
Wouldn't it be better to use the underlying, you have an underlying number behind each bit before you binarize it?
Yeah.
Seems like that's a better way to sparsify than
Yeah.
use the physical.
Like, there's a scale of value.
Yeah, but
like-
Yeah.
if you use the number, then you lose some of the capabilities of the Boolean operators. So it's, or it
Well,
makes
he's
at least
just
the
saying-
No,
Boolean
as a way to
operators.
sparsify.
Just a way to sparsify.
Yeah, but that's how it works internally. But I think also what happens if you have multiple bits, like basically there's sub-regions in here that basically say this is cat-related stuff, and this is dog-related stuff, and this is apple-related stuff. And you're
The
effectively
problem,
putting in a redundant relationship that's binary. Okay, so it's noise tolerant because it's spatially redundant. Okay, so I think that you're getting some of the advantages of having a scalar representation for each individual bit without having to have scalars.
Well,
and
okay,
do
so
all
that's-
booleans.
and another issue is that I think it is important that we are able to transfer, so to say, for example, in language. I keep talking about language. It makes it easier to make two retinas comparable. For example, this whole thing with the multilingual aspect would be much harder, I think, if this would be simply random, because the matching would be much harder. Right now, so you have words that are, so to say, sort of a translation, but no word is an absolute translation. So you use the information that you have by where the topics of these words are to keep them comparable. And basically, it's a way of compression, yeah, and of having the possibility to continuously add information. And the mapping that we are doing is just a numeric one-shot mapping. I think that in reality, what happens is that this map builds up over time. So you have to have a mechanism in keeping, so to say, the information the same while expanding the map, which is also easier, so to say, if you have a topological structure beneath the whole.
Yeah, it's quite likely that in the actual neocortex that it's not like this.
Yeah, so I was thinking, the evidence for this in biology would be.
I mean, there is some evidence because, for example, there are mechanisms that ensure that a growing nerve maintains its inner topography while it grows. Yes, so for example, if you have to get the nerve bundle from the touch sensor in the body, if that would scramble up, it would be hard if this is randomized.
The topology is very clear in the sensory region, exactly.
Yeah.
But that's different than.
And the only thing I'm claiming is that I'm taking the existing topology of the sensory region and I'm just keeping it because it's convenient.
Well, you're not really doing that because you don't really have a classic topological sensory input. You have documents and that's different.
No, we have to simulate this, of course.
Mimicking.
Yeah, I think the issue of topology of the brain, it gets really fuzzy when you get up higher up in the cortex, and it's not at all clear. And so it's really clear in the low level vision. It's very, very fuzzy when you get up higher up. So I don't know any evidence for anything like this in the brain. And now I can accept that it's useful for what you're doing. I'm just trying to understand if it's something that's basic that is required. And every time I've read and looked at it, it's very, very, no one really can find anything like this.
I mean, there could be a structural topology.
The other thing is that topology,
Yeah.
topology, at least again for language, would make the concept of the hierarchy is very easy understandable because you could create, so to say, the hierarchy by simply converging along this topology.
One could argue that this actually is going to get in the way of such representations because you're making an assumption here about what things are related, and it's going to be harder with topological connections to make connections across ideas. So it might be hard to get across, something, make connections between this and that that are separated topologically. If you spread them around sort of equally, then you have a sort of a sampling opportunity getting it. Like I think it's fine. I'm not against this at all. I'm just trying to decide whether this is a expedient thing that Protocol IO does, which really works for your type of stuff, or if it's something more fundamental. And at the moment, I'm citing in the former, but it's but that's not saying anything bad about it. It just says like I don't have to worry about it.
Yeah, right.
I thought the cross-language stuff was really cool, and if it makes that mapping easier, that's a very pragmatic way.
Pragmatic, yes. I think pragmatic. I'm always in favor of starting with theory, in general theory, and then say we can then go and do what the hell we want on top of that, right? We can go expand it.
The other side of that is that there either is or there isn't literally a spatial topography in word representations. Okay. Now, if there is, then great, you found one that maps up there.
I hope.
If there isn't, and it's just randomly spatial, okay, but structurally connected in a similar sort of way, then if it's random, then you can choose to make it topological for engineering reasons.
Yeah.
Okay, because if it's, the fact that it's either topological because evolution has designed it to be so, or the information processing requires it to be so, or it isn't, in which case you can pretend that it was, and you get a whole lot of advantage with visualization as well.
The fundamental need to have representations where similar things look similar. If you want to have this for the language representation, I don't see a way by keeping a random distribution. By a random distribution, I don't see how you can achieve this.
So, but you can
because
see
we need, for the calculation, we need this topography as, so to say, the grounding mechanism. And without this, it would not be possible.
So I can see where this
It's possible, it just would be hard.
I can see where.
Yeah, we could not compute it from existing data. I don't see how you just.
Well, if all the language retinas were trained on, essentially the same documents but translated versions, you could create a bitwise mapping from one retina
Yeah,
to
but
another.
you would not know which features to take. The fact is that we know about the features by creating a topological map. That is what generates the features.
No, but if you know that document A in English corresponds to bit 23, and that same translated document corresponds to
but
bit
it's not a
56, then you know that 23 in one and 56 in the other are related,
There
even
isn't
though
that-
they're completely separate.
there isn't that solid a connection between the two.
But that's what I was asking, is it the same set of
Extremely
translated
noisy.
documents?
It's slightly noisier than that, and noisy enough that you need to use something like that.
Here's where it's going to get, it would cause problems. If, let's say I have very large retinas and I need to use a physical topological connectivity map, as we know exists everywhere in the protein, because cells can't send their axons everywhere. And I want to learn sequences of these. Well, it's very easy to learn sequences that will stay within some context, but very difficult to learn sequences that might
It would need another.
if I want to follow Apple followed by motorcycle, whatever, and that's the sequence I want to learn, it may make it much harder to learn that.
Yeah,
If
you would need to go to a higher level to make this kind of connections.
Maybe. I have a general thing that whenever we get to hard problems, people always say, "Oh, we'll do that in the hierarchy." I don't like that as an answer. Look, I'm not pushing against it. All I'm pointing out that it's an implied assumption. I'm not sure it's supported by biology. It has some advantages, but I think it has some disadvantages as well. So I think we just have to be conscious of that and just understand what those are, as opposed to saying, it's fundamental.
Well, what I can say is that the unsupervised approach that we have here, we could not do this in a random distribution. And in general, the experience with word vectors, because this is at the end of the day, it's a word vector, without topography, so to say, they simply perform words.
All I'm saying is I wanted to take a large vectors like this and learn sequences of them using the kind of architecture that I think we need to use. It would be probably easier to do if I systematically scrambled these. And not saying how you generate it, but just physically how I lay it out.
I think that the map, so we are considering, for sake of simplicity, we are considering stable maps here. Yeah? I think personally that this map that we have beneath is constantly changing also with the experience that the brain is making. I think that it is created in this way by incrementally mapping stuff, and whenever there are, so to say, columns that have signals that co-occur, they sort of attract over time. Yeah? It's not a one-step thing.
Yeah.
Well, I think that
It's a
you can see
separate
what
part.
Jeff's talking about by you have basically a layer that looks at this and treats this as an input. So you have an SP layer that looks at this,
yeah, you could do
and
that.
that will randomize
But
the
even
topology
only
for
that will do that if my SP layer is very broadly connected. Again, my
Correct,
topology.
Yeah, but if you basically you can destroy the topology and randomize the topology.
The
putting
evidence,
an SP with big
the evidence in biology is that this is not occurring, and that it's actually scrambling as you go up the hierarchy. Not
So-
that it's technically, it's not trying to scramble.
With
Yeah,
you four
I'm
in the
not-
same
I'm
room,
not
Q&A
arguing
will never
I'm not
end.
saying you should
So-
or anything else. I'm just speaking
No,
open thoughts.
it's definitely the least, so to say, biologically supported
We just
aspect
need to
of it.
understand what it is, and we can all agree about
And
what
I'm
advantage this
I'm not
is.
convinced that this mapping actually happens necessarily at the cortical level. It could also be, so to say, in subcortical areas, like in the ganglion level or something like this. They have the structures that would allow to do this. I mean, there is this self-organizing map theory that basically works with bipolar neurons that does this mapping, and you find them at certain places in the sensorial organs. Yeah. So again, but this is the point that I'm making is that if there wouldn't be any topology, we could not have an unsupervised, at least it would simply not work that way, and we would be again
It's fine.
in the
You've created
situation
a
where we
really
don't know how to
You've
map.
created a very special organ to create these maps that is, which is really cool, but is not biological at all. And so that's a manifestation of the mathematics and the language and theory you use. And again, I'm not trying to take anything away from that. I'm just pointing out that this is I just want, in my mind, I need to put this in a framework of this is an artifact of how you did it, and you're taking advantage of it, but it has its pluses and minuses, and it's not necessarily the way it's happening in brain. But we can just leave it that way. I don't know if we don't have to debate this.
Let's leave it at that. And then we had a couple other questions from a couple guys over here.
My question was not fuel with fire, sorry.
Oh.
Actually, I was saying the question does not fuel with fire. Can you talk about the other retinas that the other retinas that you trained and how they map into each other? Because you mentioned some of the different language retinas, and there's some overlap.
So in a very general fashion, the retina is basically the place where you can store experience. Yeah? So we simulate with the retina what an individual, for example, has learned based on language, of course, on a certain topic. And so this can be used as a mechanism to produce special purpose retinas. Yeah? So you can take specific inputs to create specific representation for specific areas.
Right, so given a corpus of text, right? So I can look at, I don't know, all the books of law and then compare all those to all the medical records that we've trained, and there would be different representations, some would overlap. I'm just curious, which ones have you trained so far, and what are the
Well, we have basically used Wikipedia, so we wanted to have sort of the general language situation. So from the content, it's mostly Wikipedia, only Wikipedia data, and we will have also experiments in using other more encyclopedic type of data. Because that's easier, because it has a structure to be very explicit about something. And if you have the pieces of text to be explicit about something, they're very useful to actually create retinas from.
And you haven't tried, the data set you've always been going over is rather large, so that there's a lot of context for it. Have you tried anything where it's actually a very small data set and found that useful in that particular context?
No, it has not necessarily something to do with the size, because although you might want to create a retina for law, you still need all the normal words also. So there is some sort of basic set of language that you always need, and that is, if you want, what is captured in Wikipedia. So I would rather regard it as additional information that is trained on top of the Wikipedia.
Right, so you wouldn't train only on the law texts. Like if you train on only the law text, you'll never understand what the word apple means except in the context of some examples, but you would have a very good understanding of what jurisdiction means.
Yeah, but if you then actually read documents with the system, real-world documents, Apple might appear there. Yeah?
Right.
So that would produce holes in your interpretation, and you could maybe still say something about the law aspects, but I think it's necessary to have this complete picture. Yeah? As a human cannot start by going to the university without going to school before. Yeah? So that's... Yes?
So you have this map of 16,000 features, and I'm just wondering, how do you choose the features? Are they different for each retina, or do you have some...
They are specific for a retina, and they are generated using machine learning, basically. It's a machine learning approach that tries to sort of distribute the contexts that are extracted from the documents by which I want to train the retina. So these are like the universe definition documents, and we cut them in pieces, and we, so to say, bring all the NLP mechanisms that we know, try to apply this there to create the retina, and the ideal case, we don't ever touch them again. So we use a lot of things like TF-IDF to compute the retina itself, but after the existence of the retina, we try to rather not use it anymore and only use sort of Boolean and similarity operations.
I think we have a tape of you explaining how this works.
Yeah.
I think a couple of hackathons ago.
Yeah.
Very cool.
Online.
It's in German
a couple times.
So just a quick question. So on the topic of retina creation, as a user, is it possible right now for someone to come in, customize a retina based on whatever context they want to feed in, and then use that retina as they see fit?
So currently, no. So what we do is that we do that in, so to say, our commercial operations.
Okay.
We create specific retinas for people who want to have a very precise use of this. But that's basically the idea, to use this as the, so to say, commercial aspect of it. So we could do this by working together. That wouldn't be a problem, even if it's not in a commercial fashion. But we right now don't. It's basically it's a cooking recipe. I mean, we have been trying out this stuff for a certain time, and so there is some know-how that has built up on how to create this very special dish, and that's what we try to basically use as a foundation. But the advantage is that if you if it doesn't matter to you, so to say, how the retina was created, everything from there is open. We sort of give away anything that sort of sits on top of that, and that is open, and that will stay like this. So the actual technology will be always available for everybody.
Thank you.
So can you tell something about the current businesses it's used in, and have you ever applied it to search, maybe, like indexing large sites and using everything in it to create a retina and search on top of that?
Yes, of course. We are actually working on a model of using this for search, because as you can imagine, a similarity function is sort of the optimum case for searching. You can provide, I might even have a explanatory image here. There it is. The mechanism is as follows. You specify a query by giving an example document that is converted into a fingerprint. You have an index of n fingerprints in your repository, at least one per document. Typically you have several fingerprints per document. And by doing a pure Boolean similarity calculation, you can get the match, and you can easily rank according to the distance. You might know that ranking with traditional methods is in reality not that easy, because there is no so to say, inherent similarity. So you have only the, so to say, TF-IDF, for example, to use for ranking, but that is sometimes problematic. Sometimes what we have here as a possibility for search is that we can even capture the interest of a user by having the user choose a handful of documents that represent something that is specifically interesting to him. Again, you create the fingerprint, and now you can create a result set by selecting, again, the query with documents, but instead of directly ranking it to the distance, you measure the distance to the profile fingerprint. And that allows you basically to have the same query on the same documents, give two different results depending on which user actually is trying this. And we are experimenting with this for a while now. And in the end, I think we will implement this as a plugin, for example, for Elasticsearch or so, where you actually have the similarity plugin, and you can plug in whatever algorithm you have for it. So this would be a way in doing this. I personally think that the current implementation is very static. So we use the plain fingerprints, and in the next step, we want to use the HDMs to actually create the fingerprints, and I think they will be sufficiently smart to basically not make reasonable results, but to make very good results. To use this search. And yeah, and we have other customers and people who are about to become customers using this, interestingly from very different fields. We have people in e-learning who use this to synthesize personalized examples for e-learners online. We have people from the SEO space who use this to optimize your content to get high rankings with Google. So there's a lot of funny applications. In HR, for example, you can match job seekers and job descriptions. And instead of having SQL data, so to say, that has to be matched and categorized, you can actually match the plain writing of the job seeker and the plain writing of the job description and match this and things like that. Yeah.
How did you settle on 128 by 128? Have you experimented with like 64 by 64? Do they give you more general results? Do you get them to fit into 256 by 256?
Yeah. So it's basically there is no real rule behind it. The algorithms allow to do this as you wish. The bigger it becomes, the longer it takes to compute, and the longer every processing, of course, takes. And we have found that using at least general English, the 128 is somehow a good mix of how complex you make it and how simple you keep it.
Have you been able to generalize? So if you get the representation like 128, right, and if you scale it down to 64 by 64, maybe even scale it even further down by 30 by 32, and then bring it back out to 128, do you get a very set of generalized terms?
No, it's not that simple. But what you get, first of all, you can actually do this, and that would be a problem if we would not have topology. We could not do this zoom, by the way. But it's not as simple as saying that the terms get more general, but they get more, you are less sure of which of the context terms actually get selected.
So it's not actually that good. It's not beneficial. It's actually more muddling.
Yeah, it could be beneficial if on a specific topic the variations wouldn't be that big. You could save a lot of time of making it smaller. So one of our experiments was actually to feed smaller fingerprints into an HDM, and by having the HDM also consider the dynamic aspect, if you want, you could possibly afford to make it smaller. So many of the experiments also work nicely if you take smaller versions of it. But as we have right now, still sort of an emphasis on the pure static use of it, the 128 seems to be sort of a natural level.
Okay. Any more questions? Thanks, Francisco Weber.